Hello friends, welcome to our YouTube channel. A complex electrical network can easily be analyzed if we consider it as an interconnection of several smaller and simpler modules. This not only helps to solve the problem but also reduces chances of error. Designers, when design a complex network, they design simple two-port modules and then interconnect them. This leads to error-free design and makes things simpler. It is also easier to shield the smaller units to reduce the parasitic capacitances to ground. A variety of interconnections are feasible. Today we shall discuss parallel connection of two-port networks. Two-port networks can be interconnected in various ways. When we connect output port of one two-port network to the input port of another two-port network, we call it cascade connection. It is the simplest method and a very popular one. The overall transmission parameter matrix for cascade connected two-port networks is the matrix product of the transmission matrices of each individual two-port networks. The overall inverse transmission matrix for cascade connected two-port networks is the matrix product of the inverse transmission matrices of each individual two-port networks but in reverse order. When both input ports and output ports are connected in series, we call it series connection or simply series connection. The overall Z parameter matrix of series connected two-port networks is the sum of Z parameter matrices of each individual two-port networks connected in series. When both input ports and output ports are connected in parallel, we call it parallel connection or simply parallel connection. The overall Y parameter matrix of parallel connected two-port network is the sum of Y parameter matrices of each individual two-port network connected in parallel. When input ports are connected in series, output ports are connected in parallel, we call it a series parallel connection. The overall hybrid parameter matrix of series parallel connected two-port networks is the sum of hybrid parameter matrices of each individual two-port network connected in series parallel fashion. When input ports are connected in parallel, output ports are connected in series, we call it a parallel series connection. The overall inverse hybrid parameter matrix of parallel series connected two-port networks is the sum of inverse hybrid parameter matrices of each individual two-port network connected in parallel series fashion. Today we shall talk about parallel connection. Now let us see how we can connect two two-port networks in parallel connection. We have a network A having short circuit admittance parameter matrix YA and its input and output port voltages are V1A and V2A respectively. We have a second two-port network B having short circuit admittance parameter matrix YB and input and output port voltages V1B and V2B respectively. Let us connect the input ports in parallel connection, and the input port voltage of the combined network is V1, that is equal to V1A equals to V1B. Let us connect the output ports in parallel connection. The output port voltage of the combined network is V2 and that is equal to V2A equals to V2B. Let us assign the input and output port currents of the combined network and network A and network B. Let the input port current of the combined network be I1 and the output port current be I2. The input and output port currents of network A are I1A and I2A respectively, and the input and output port currents of network B are I1B and I2B respectively. By applying Kirchhoff's current law at the input port, we can write I1 equals to I1A plus I1B. By applying Kirchhoff's current law at the output port, we get I2 equals to I2A plus I2B. Now let us derive the overall Y-parameter matrix for two parallel connected two-port networks. When we describe any two-port network using Y parameters, we express the input and output port currents I1 and I2 in terms of input and output port voltages V1 and V2. For network A, we can write I1A equals to Y11A V1A plus Y12A V2A, and I2A equals to Y21A V1A plus Y22A V2A. For network B, we can write I1B equals to Y11B V1B plus Y12B V2B, and I2B equals to Y21B V1B plus Y22B V2B. For the combined network, we can write I1 equals to Y11 V1 plus Y12 V2, and I2 equals to Y21 V1 plus Y22 V2. As the input ports are parallelly connected, applying Kirchhoff's current law, we can write I1 equals to I1A plus I1B. Using the expressions of I1A and I1B, we get Y11A plus Y11B times V1 plus Y12A plus Y12B times V2. Because for parallelly connected input ports, V1A equals to V1B equals to V1, and for parallelly connected output ports, V2A equals to V2B equals to V2. Applying Kirchhoff's current law at the output ports, we can write I2 equals to I2A plus I2B. Using the expressions of I2A and I2B, we get Y21A plus Y21B times V1 plus Y22A plus Y22B times V2. Comparing the expressions of I1, we get Y11 equals to Y11A plus Y11B, and Y12 equals to Y12A plus Y12B. Comparing the expressions of I2, we get Y21 equals to Y21A plus Y21B, and Y22 equals to Y22A plus Y22B. Therefore, we can write matrix of Y equals to matrix of Ya plus matrix of Yb. Hence, we can conclude that the overall Y parameter matrix of parallel connected two-port networks is the sum of y-parameter matrices of each individual networks connected in parallel fashion. This result may be generalized for any number of two-port networks connected in parallel subject to the condition of interconnectibility being satisfied. Let us solve a numerical problem. Here we can see a resistive network. We have to find the y parameters of the network shown. Here two networks are connected in parallel fashion. We can see network A and network B, both are T networks connected in parallel connection. We know for any T network comprising of ZA, ZB and ZC, we get Z11 equals to ZA plus ZC, Z12 equals to Z21 equals to ZC and Z22 equals to ZB plus ZC. Therefore, if we take out network A, we get Z11A equals to 3 plus 2 equals to 5 ohm, Z12A equals to Z21A equals to 2 ohm, Z22A equals to 2 plus 2, that is equal to 4 ohm. So we can write matrix of ZA equals to matrix of 5, 2, 2, 4. Now, if we take out the network B, we can write Z11B equals to 2 plus 1 equals to 3 ohm, Z12B equals to Z21B equals to 1 ohm, Z22B equals to 2 plus 1 equals to 3 ohm. Therefore, we get matrix of ZB equals to matrix of 3, 1, 1, 3. So now we have matrix of ZA equals to matrix of 5, 2, 2, 4, and we obtained matrix of ZB equals to matrix of 3, 1, 1, 3. Therefore, matrix of YA equals to inverse matrix of ZA equals to inverse matrix of 5, 2, 2, 4 gives us matrix of 0.25 minus 0.125 minus 0.125 0.3125. Matrix of YB equals to inverse matrix of ZB, that is equal to inverse matrix of 3, 1, 1, 3, that is equal to matrix of 0.375 minus 0.125 minus 0.125 0.375. We know the overall Y parameter matrix of parallel connected two-port networks is the sum of Y-parameter matrices of each individual two-port networks connected in parallel fashion. Therefore, matrix of Y equals to matrix of Ya plus matrix of Yb. Therefore, we get matrix of 0.25 minus 0.125 minus 0.125, 0.3125 plus matrix of 0.375 minus 0.125 minus 0.125, 0.375. That gives us matrix of 0.625 minus 0.25 minus 0.25, 0.6875 more. So, today we have learned that when both the input and output ports are connected in parallel, we call it a parallel connection. We have derived the expression for the overall Y-parameter matrix of two parallel connected two-port networks. We have found that the overall Y-parameter matrix of parallel connected two-port networks is the sum of Y-parameter matrices of each individual networks connected in parallel connection. That's all I have for you today. Hope this lecture has been useful for you. If you have any question or suggestion, please drop it in the comment section below. If you have liked this video, please give it a thumbs up and share it with your friends. Thank you.